Okay. So I spent a little more time working on this, and I got to a solution. This is so the problem is converting a fraction to a recurring decimal to a string form of recurring decimal if the fraction is non-terminating. So yeah, you're given a numerator denominator, which I kind of related to P and Q for to make it shorter. P divided by Q is a normal kind of fraction notation. And then, yeah, if it's a terminating fraction, then just return it without any repetition. If there's any repetition, then denote the repetition as parentheses around whatever is repeated. It's like same as having a bar over those terms, over those digits. And so I did get a solution. I'm going to try to explain the math behind it, but honestly, there's likely is a much better way of interpreting this than what I came up with. But the first part here is pretty straightforward. So P and Q could be both negatives, and if they're both negatives, then they're equivalent to being both positive. But with some of the math that I did, it's easier to just handle it in the positive sense. Or if one of them is negative, one is positive, then it's a negative fraction, right? So I'm just going to return the negative symbol in front of the fraction where I treat the fraction as a positive fraction, positive P, positive Q. Alternatively, if both of them are negative, which is the else here, if both of them are negative, then just return the absolute value of the positive version. Yeah, just ignoring negatives at all in the P and Q. The other case is kind of a trivial case where if your division results in no remainder, then there's no need for a decimal, so just return the string of how many times Q goes into P, the denominator goes into the numerator. So for instance, the example 2, this will just return 2, string 2. And then this is the last case, which is if if this is a improper fraction, there's this improper fraction inclusive in addition with the 1 split answer to kind of mixed fraction, whole and part, whole and decimal part. So like if you're dividing 10 divided by 3, then, or 10 divided by 4, 11 divided by 3, then it'd be how many times 3 goes into 11, which would be like 3 times. And then the remainder is going to be 11 mod 3, which is 2. So it'd be 3 and 2/3. So you're going to return the string 3 and the fraction of the string that is 2/3, where I use 2/3 calling on this function again. Remainder 2, Q is 3, and then this will give me something that is like 0 point something. So it'd be the whole number point whatever that would give me. So that's all kind of you don't have to worry about, as long as the method itself is working, then you can assume that that has to work. Okay, the trickier portion is how to handle, like, the rest of this is for a numerator that's smaller denominator, how to convert that to a like 0 point something repeating. So the logic here is going to be, like in this example here, 199 divided by 12, that's 16 and 7/12. The 16 is the whole part, the remainder is 7, and then 12 is the cube, the denominator. 7/12, if I want to convert that to a repeating fraction, I'm going to think of that as, or repeating decimal, I'm going to think of that as 1/4 times 1/3 times 7. 12 is broken up into 4 and 3. Now, in particular, the breakup is into any factors that are convertible to 100. So any factors that are 2 or 5 is within this first fraction. So 12 has factors of 2 twice, so it's 1/4. And then the remaining factors is 1/3. So 1/4 can be converted to be 25 100ths. And you can do that by taking 100 divided by 4, or even 1,000 divided by 4, and you get 250 over 1,000, which again simplifies to be 25 or 100. This is key because the 100 is the number 100, which is 10 to the second power, denotes the number times the decimal moves over, or the number extra zeros that would be in front of the repeating portion of the decimal. So anyways, this 1/4 gets converted to be 25 100. And then you're left with the 1/3 and the 7. And then, or you're left with the 7/3, I guess. Now you can move it around and say the 100 is dividing this whole expression here, the product of 25 times 7/3. 7/3 is going to be something that is actually repeating. Anything that doesn't have a factor of 2 and 5 can be converted to something that's a repeating decimal. So one kind of trivia is that the repeating decimal is the portion that repeats can be written as a fraction, where that portion is the numerator over some number of 9s. So repeating digits in decimal can be written as those digits over 9s. So for instance, if this was like 117 repeating, so like 0.777, 0.171777, this is going to be the same thing as 17 over 99, or something simple like 0.2 repeating, 22222. That's going to be 2 over 9. If this was like 0.15 repeating, that would be something like, that would be equivalent to 135 over 999. So in case, what you want to do is you want to find, you want to convert the fraction here to be something that, to be a fraction that is possibly over 9s. So 1/3 can be converted to be something over 9. Or if it doesn't work, then you extend it out to be like over 99 or over 999. Keep on extending this out until it actually works. But 1/3 is equivalent to something over 9. X would therefore be 9 over 3, which is going to be 3. So 7/3 converted to an equivalent fraction would be 21 over 9. So this is the same thing as 25 times 21 over 9 over 100. The 25 times 21 is 525 over 9, all over 100. Again, this 100 just changes where the decimal is. 525 divided by 9 in terms of like whole part and fraction part is going to be 58 and 3/9. 3/9 is a 3 repeating. So this is 58, 3 repeating divided by 100. So this is going to be like 0.58 repeating, right? So 7/12 is 0.58 repeating. All right, I'm going to do that for one more just random example. Let's say this is 415. I'm going to be doing this over, actually let's say 413 over 15. So 413 over 15 is 27, and 27 times 413 minus 27 times 15. So this is 27 and 8/15. So the answer is going to be 27 dot, then whatever 8/15 converts into. Now 8/15 is the same thing as 1/5 times 1/3. 1/5 is 100 divided by 5 is 20. So 1/5 is the same thing as 20 over 100. Whoops. 1/5 times 1/3 times 8, I guess. So this is times, let's say, 8/3. So rearranging that, that's 20 times 8/3 divided by 100. Again, x over 3, or 1/3 is the same thing as x over 9. X is going to be 9 over 3. So that's going to be 3. And so 8/3 becomes 24 over 3. So it's 20 times 24 over 3. No, sorry, 24 over 9. Divided by 100. 20 times 24 is 480 divided by 9 over 100. 480 divided by 9 is 53, and it's 3/9 divided by 100. So this is going to be 53 through repeating divided by 100. So it's going to be 0. You could actually do 5/3 or 0.53 through repeating. Alright, those work here. So 480 divided by 9. Did I miss something? No, 4. The original was 413. 413 divided by 15. So it's 27.5 through repeating. So yeah, the 8/15 converts into that portion of the decimal, that repeating portion. In any case, so that's the math behind it. The way that that's done is you have your numerator and denominator. This is for just the fraction portion. I remove any common factors of those, so kind of reduce the fraction. I find the number of 2 multipliers within it, within the denominator. Find the number of 5s, or keep track of those. Divide the denominator. In this case, the denominator being like the 15 here, or the 12 here. It's the divisor of the denominator of the that's being called for the fraction. So divide the factors of 2 and the factors of 5 out, keep track of how many factors of 2 and 5 there are. That's the multiplicity. The conversion, like how many times you would need to move the decimal over, is based on that. So the power of 10 is based on whatever is the bigger of those two values, bigger of those two multiplicities. And then the factor that you multiply would be 10 to that power divided by the 2 to whatever number of 2's there are, 5 times 5 to whatever number of factors there are there. So that gets you like the 25, which is like 10 to the second power divided by 2 squared, or that gets you the 20, 10 to the second power divided by 5 to the first. That gets you that number 20. So that's that factor. The other one is for the repeating fraction. So I assume the repeating fraction is going to be something over 9. Denominator is going to be 9. The number of 9's within that denominator is going to be 1 currently. And then while that number is not divisible into the q, in this case q is currently removing all the 2's and 5's, so currently like 3. If it's not divisible by that, then you increase the number of 9's in your denominator, and it eventually will find it. So like if your q was originally, after you remove the 2's and 5 factors, like 7, then eventually there's some number that has repeating 9's that's divisible by 7. So then you'd find the actual factor, which is that value, how many times it goes into it, times the previous factor. The numerator is going to be p times factor, denominator is going to still be q. The whole number is going to be num divided by denom. Repeating portion is num mod denom. Again, denom is repeating 9's. And then you get your whole portion of your string, fill it with zeros in front, depending on the power of 10s that you have to deal with. So if this was like, let's say instead of this being yeah, you have to fill in with the zeros in front. What's a simple example there? I guess the simple example, which was the one that I got stuck on, would be something like 4 divided by, let's say, 333, which is the same thing as 4 divided by or 333 is the same thing as 1 over 111 times 1 over 3. Actually, that's not the one that stuck me. Oh gosh. What was the one that stuck? Okay, let's say it's 4 divided by 2, 300. Yeah, 4 divided by 300, sure. So 300 is the same thing as, oh, but that's reducible, right? You can divide out, and that's the same thing as 1 over 75. Okay, I guess, sure, 1 over 75. So that's the same thing as, there's 2 5's there, so it's 1 over 25 times 1 over 3. 25, 1 over 25 is the same thing as 4 over 100 times, eventually 1/3 converts into 3/9. And then you move it around, 4 times 3 is 12, divide by 9, plus divide by another 100. And then 12/9 is 1 3/9, divided by 100. So this 100 here moves the decimal over. So this is like 1 3 repeating. Move the decimal over 100 by 100. So instead of it being 0.1 0.03 repeating, it's going to be 0.013 repeating. 0.0133. So yeah, power of 10 that you're dealing with gets you to leading zeros. So it'd be 0.01 3 repeating. So the power of 10 that you're dealing with here is the number of digits, including leading zeros, that you should have after the initial point, or the non-repeating portion of the decimal. And then similarly, the repeating portion of the decimal will have some leading zeros that are based on the number of nines that you're dealing with. So for instance, if you're dealing with like a repeating 0.120035, where the repeating is 00350035, here the repeat value is going to be 35, but the number of nines that you're dealing with is 4, like 9999. In any case, yeah, that's my code. Summary, this is way too mathy to really explain, but the above works. Time complexity, this was, well, it's pretty much constant, really. As there are some loops to determine how many factors of 2s or 5s there are, but those are very finite. So like, yeah, at most 30 loops maybe, since you're dealing with 30-bit integer. So overall, very fast. And then space complexity, this is, you have a string. I don't think I need to use anything extra here. No extra space was used. The string was created with minimal concatenation. Yep. And yeah, the speed is like, I assume everything that works here should be, wow, that was not what I expected. This is, I think, random.